Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss complexes which have multiple bonds between metal and carbon. We have already seen carbon monoxide and a few other ligands, and I have shown this in this ligand map which I have drawn. So, you can see that carbon monoxide occupies a unique place. Carbon monoxide occupies a unique place in the ligand space. So, there are some derivatives of carbon monoxide such as the cyanide, which I am highlighting here, which have a special ability to transform in the coordination sphere of the metal to some other ligands. We have seen this in the lecture on N heterocyclic carbenes. So, you have isocyanides which are CN derivatives, and these isocyanides can be converted into Fischer carbenes, which are in turn related to N heterocyclic carbenes, the nucleophilic heterocyclic carbene which we discussed in the previous lecture, where the carbene is in fact stabilized by resonance from electron donation, which is coming from the heterocyclic atom. You could also have a acyclic system, where the carbene carbon is stabilized by donation from the heteroatom. So, in the lecture on N heterocyclic carbenes, we encountered carbenes which have got two nitrogens or two heteroatoms, and these are the two heteroatoms that we are talking about. These two heteroatoms are stabilizing the carbene carbon, which is having a pair of electrons which can be donated to the metal atom. And perpendicular to the plane in which this lone pair is positioned, perpendicular to this plane, there is a vacant p orbital which is in resonance with the lone pairs on the two nitrogens. So, this is the factor which stabilizes the carbene carbon. So, stability through conjugation is an important factor and is in fact essential for the stability of these carbenes and the stability of their complexes. But there is yet another factor which stabilizes these carbenes, and that is a fact that you have rather large bulky R groups which are situated adjacent to this carbene carbon. So, stability is achieved through steric protection of the carbene carbon. It is also achieved through conjugation of the vacant p orbital on the carbon with the nitrogen lone pairs. And these complexes are stabilized because of pi acidity. When the metal forms a complex with the carbene, it has two interactions which are typified by donation from the lone pair that we referred to, and there is a back bonding as in the Dewar, Duncanson chat model. From the metal, there is some dative bonding which occurs, which pushes electron density in the opposite direction. These two factors stabilize the complexes. So, we also encountered in the lecture in heterocyclic carbenes the fact that there can be stabilization through aromaticity, and this stabilization through aromaticity comes about because if you have an extra pair of electrons as in a pi system which is in resonance with the two lone pairs on the nitrogen, then you have a total of 6 pi electrons. and the 6 pi electrons are the ones which lead to an aromatic ring system, and it stabilizes the carbene to a great degree. So, there is stability through steric protection, stability through conjugation, stability because of the aromatic system that is formed in this ring system, and all these factors stabilize the carbene. In addition, the carbene, when it complexes to the metal, is stabilized because of pi acidity, or the type of Dewar-Duncanson-Chat resonance which occurs. From the metal, some electron density is pushed into the carbene carbon. So, these are N heterocyclic carbenes, and they occupy a special place in the literature. And today, I want to introduce to you a related system, which is a system which has been called an abnormal carbene complex. There is nothing really abnormal about these carbene complexes, but we will explain how they are slightly different from the N heterocyclic carbenes that we discussed just now. You will remember that the stability of the carbene itself is coming from several factors. All these factors can be maintained, and still there can be a slight variation. Just imagine that you have, instead of the carbene anion or the lone pair on the carbene carbon being situated on a second carbon, which is not the one between the two nitrogens. So, it is not this nitrogen which is holding the lone pair or the pair of electrons, but let us assume that it is this carbon. In this instance also, you can have stabilization due to aromaticity, because you still have 6 pi electrons. Those 6 pi electron system is the 6 pi electron system is not affected when you move the lone pair of electrons from this carbon, which is usually the C1, to the third carbon atom, which is this carbon atom. So, moving the pair of electrons from the place where it was originally present in the N heterocyclic carbenes to a different place is not affecting the stability of the system in terms of aromaticity. In fact, it is going to be equally aromatic, and it can have pi acidity as in the previous system. So, all those situations are still maintained, but it is abnormal because it is different from the usual place where it is formed. So, how can one move this pair of electrons or this carbene carbon from this position 1 to position 3? This can be done if we block it with an R group in the appropriate position. So, instead of a hydrogen, if I have an alkyl group in this position, then in the first position, as shown here, as it is shown here, if I have an alkyl group which is placed in carbon atom 1, then the carbon atom 3, if it bears a hydrogen atom, it can be deprotonated and a carbene carbon can be formed. You will remember that it was only 10 years ago, before 2009. So, it was in the year 1999 that you had the synthesis of the first N heterocyclic carbene. So, the anomalous heterocyclic carbene or the C5 deprotonated imidazolium N heterocyclic carbene was discovered in 2009. So, the way this was carried out was by taking N substituted N alkylated ring systems along with both the C1 carbon here and the C5 carbon. Both of them were in fact substituted with phenyl groups, and a hydrogen was positioned in this place, and it was deprotonated using a very strong base, which will abstract the proton present in this position. So, the base that is used is trimethylsilyl substituted bis trimethylsilyl amidate anion, and the bis trimethylsilyl amidate anion is particularly suited for deprotonation rather than nucleophilic attacks. because of the very bulky nature of the two trimethylsilyl groups which are present on the nitrogen. So, if it was less bulky, then a nucleophilic attack could have been made on this on this positively charged ring system which is present here. So, having protected the two nitrogen atoms with very bulky groups, that is the 2,6-diisopropyl phenyl group which is pictured here, which has been abbreviated to DIP. This is the 2,6-diisopropyl phenyl group which is present here, and it is connected to the nitrogen atom through this carbon. And you can deprotonate now this ring system on this only carbon which is bearing this hydrogen. So, you form a carbene carbon. Now, this has got both a positive charge delocalized here because of this nitrogen lone pairs which are delocalized into this carbon, and it has this negative charge which is in the plane perpendicular to the plane of the pi system. So, let us see what happens if you take a crystal structure of these molecules. You find that this is the original molecule which has been also crystallized and characterized. It is a imidazolium cation, that means it has got a net positive charge. But when you deprotonate it using the NN dialkylated or the diisopropyl amidate anion, then you can deprotonate it only in this position. So, you deprotonate this carbon and you end up with a carbene which is pictured here. The lone pair is in the same plane as the ring system. So, there is a pair of electrons here, and that is the carbene carbon. But now, we call it abnormal only because you have the usual carbene carbon bearing a phenyl group now, and the unusual position for the carbene carbon is in the third position. It is stabilized only by the vacant p orbital on the C3 is on the C3 atom has got a vacant p orbital, that is stabilized by the pair of electrons which is present on N1, but it cannot be stabilized by the lone pair which is present on N2. Nevertheless, this now forms a carbenic system, and it can be coordinated to the metal atom, just like we coordinated the normal N heterocyclic carbene. So, these are called ANHC, and that is pictured here, abnormal N heterocyclic carbene. But you can notice one thing, the two structures are extremely similar. The two structures which are pictured here, this is the imidazolium cation, this is the imidazolium cation here, and the carbene are extremely similar. And that is because the pi system, which is perpendicular to the plane of the ring, is not affected by this deprotonation, and the lone pair that is available for donation to the metal atom is present perpendicular to the, it is in the plane of the ring system and perpendicular to the plane of the pi system. So, these two, the carbene and the imidazolium cation were characterized perfectly using single crystal structure determination, and so we have a good idea about how the bond distances vary in these ring systems as well. What is interesting is that these compounds, which is the carbene, abnormal N heterocyclic carbene, is equally capable of forming a metal complex. Pictured here is only the gold complex. The gold complex is formed by simply treating the carbene with AuCl, that is gold monochloride, that is a gold 1 oxidation state, and that forms a very nice complex with this carbene, abnormal N heterocyclic carbene. What is interesting is that this molecule also interacts with carbon dioxide to form a carboxylate anion, and this carboxylate anion is interestingly, it is exactly the reverse. It is a structure that was used to prepare the normal N heterocyclic carbene by decarboxylation. So, the reverse reaction was known for the preparation of N heterocyclic carbenes, but now we find that this molecule is reactive enough, to react with carbon dioxide to form a carboxylate anion. So, let me just summarize what we have just been discussing. N-heterocyclic carbenes are great ligands because they can have different donor properties depending on the ring system that is there. You have tunable electronic property. You also have tunable steric property because the substituents of the nitrogen can be changed. What is interesting is that the ligand is easily synthesized many times in situ. It can be synthesized and reacted with a metal atom. And they are superheroes primarily because they have been shown to have very good catalytic properties, and these catalytic properties we will be dealing with towards the end of the course. The abnormal N-heterocyclic carbenes that we just saw can also be synthesized very easily in the coordination sphere of the metal atom, and they can be synthesized as isolable carbenes also. And so, they have been touted as very interesting species which can be used for catalysis. However, at the moment not many abnormal N-heterocyclic carbenes are known. What characterizes both the NHC and the abnormal NHC is the fact that they have very good sigma donation, much better sigma donation to the metal than carbon monoxide itself, and so their properties are significantly different. Now, I want to move on to another topic which is related, and I will show you how they are related. The topic that I would like to discuss is the fact that you can have compounds where there is a metal carbon double bond, and these carbene complexes are in fact stabilized by a heteroatom which is attached to the carbene carbon. So, here I have shown you the reaction that led to the heteroatom stabilized carbene complex. If you take the metal isocyanide compound, this is a metal isocyanide complex. We noted that there is a resonance structure which can be written as a M double bond C double bond N, and in this structure you have polarization of the carbon as delta plus and the nitrogen as delta minus because of the electronegativity differences. And because of these differences, you can have a nucleophilic attack by the ethanol, which is used as a solvent on the carbon. So, this nucleophilic attack leads to the formation of a molecule which I told you is a disadvantage because you can't use the isocyanide itself. It very often reacts with a solvent or with a nucleophile and generates a different molecule altogether. But this molecule by itself is a stable species very often because you have a carbenic carbon which is stabilized by two lone pairs, just like you have these N-heterocyclic carbons which are stabilized by two nitrogen atoms. So, what I want to emphasize is the fact that the abnormal N-heterocyclic carbene carbon is stabilized by only one heteroatom, only one nitrogen, and it was still forming a nice complex with the metal. And here we have a system where when the carbon is polarized in a positive fashion, you can have an attack by a nucleophile. So, if you combine these two factors together, then we have a new system which is being formed. Let us look at one of the resonance structures of a carbonyl complex, and here is a carbonyl complex which I have written here with the same type of a resonance structure LNM double bond C double bond O, and this should also be polarized such that you have a small positive charge on the carbon and a small negative charge on the oxygen. So, in this particular resonance structure, you can have a nucleophile attacking the carbon which is the carbonyl carbon. If I treat tungsten hexacarbonyl, which is pictured here, tungsten hexacarbonyl, which is pictured here, if I can treat it with N-butyl lithium, the butyl lithium is a good nucleophile and it will attack this molecule at the positively charged center. In this particular molecule, it happens to be the carbon. And so, one would form an intermediate where the R group, which is the butyl group is attached to the carbon, which is originally from carbon monoxide. So, you can have an intermediate in which the negative charge is pushed on to the oxygen and the carbon is attached to the R group or the alkyl group, which originally came from the alkyl lithium. So, you have a negatively charged species. You can now treat it with trimethyl oxonium ion. This is trimethyl oxonium ion, which is a good donor of methyl cation, which is a convenient source for methyl cation. This methyl cation will now react with your O minus species, which is present here. And so, we form a new complex now, which is a molecule which can be called the Fischer carbene, because Fischer was the first person who made these molecules, and these were characterized long before N-heterocyclic carbenes. However, we have looked at these in the light of the reactions that can happen with isocyanides, which are coordinated to the metal. So, there is a conceptual relationship between the two. An isocyanide is also polarized with a carbon bearing the positive charge, and a carbon monoxide is also polarized with a positive charge on the carbon when they are both coordinated to the metal atom. Once this happens, you can have a nucleophilic attack, and that nucleophilic attack can be used to generate a carbene complex, which is this particular species which I have pictured here. So, let us now move on to the hexacarbonyl chromium complex. I have just pictured it here to show you that one normally does not write the carbonyl complex as a metal double bond C double bond O structure. That makes it look very awkward, because we are not used to chromium bearing 12 bonds as it is pictured here. But we have to bear this in mind, that there is partial double bond character between the metal atom, which is in the center, which is attached to the carbon monoxide. So, the chromium carbon distance, for example, in this case is 2.04 angstroms, and this 2.04 angstroms is in fact, this 2.04 angstroms is much less than what you would expect for a single bond. I want to emphasize this fact, because we are going to look at some more complexes today, which will have bond distances which are less than what you would expect, but they may not be perfect double bonds. So, this double bond character which is there in the chromium hexacarbonyl is responsible for the nucleophilic attack that can take place between alkyl lithium onto the carbenic carbon, which is in fact a carbonyl complex in this particular instance. So, the first thing we note is that X-ray shows that the bond distance is much less than expected. So, there is in fact a double bond character. Secondly, we note that proton NMR of molecules which are pictured here, that is a Fischer carbene pictured here, shows that there are two distinct isomers for these molecules. And these two isomers come up because the methyl group which is attached to the oxygen has two different environments, depending on whether it is closer to the metal system or away from the metal system. In this isomer, it is shown away from the metal system. Here, it is shown closer to the metal system. And that happens because you have partial double bond character, which I am indicating here. So, if this CO bond has got partial double bond character, then you can have two distinct isomers, as I have shown you here, which might be pictured as syn and anti isomers. So, it is very clear that this double bond that we draw is in fact a partial double bond, and this partial double bond is responsible for the presence of two isomers. if you look at carbon 13 NMR, you also find out that there is some carbenium ion character in this chromium hexacarbonyl and in the Fischer carbene complexes, because the value for the carbenium ion is quite high, the chemical shift is quite high, and that is indicative of depletion of electron density around the carbon. So, these Fischer carbene complexes are those systems where you can have metal carbon double bond character, and that is possible because of the fact that you have a carbene carbon which is diamagnetic, and it has which has a pair of electrons in the orbital, which is like an sp2 hybrid. This can be called as an sp2 hybrid, and the p orbital, which is perpendicular to the plane in which the 3 groups are present. These 3 groups are present, is an empty p orbital. This p orbital is empty, and you have a pair of electrons in the sp2 orbital. So, now you have a system which can both donate electron density to the metal, and it can accept electron density from the metal into the p orbital, very much like carbon monoxide. And so, you have partial double bond character in the Fischer carbene also. So, let us now look at some examples where you can synthesize these carbene complexes. Apart from the fact that you can generate them by a nucleophilic attack on carbon monoxide, it is also possible to employ other techniques. And here I have shown you the sodium salt of CrCO6. If you take chromium hexacarbonyl, and react it with sodium amalgam, you can pump in electrons into the CrCO6, and this results in the formation of Na2CrCO5, and this salt is extremely nucleophilic, and it can carry out nucleophilic attacks on a carbon center which bears 2 chlorine atoms here. So, if you do a nucleophilic substitution from by using the electron density which is present on chromium, if you make an attack on this carbon which is present here, this pyrocyclic looking carbon, then you can remove the 2 chlorines successively to form a carbene complex, which is pictured here. So, this carbene complex now has got a cyclopropenium character also, and it is quite stable, and you can synthesize a limited number of complexes in this particular fashion. Nevertheless, this just illustrates the fact that there are other ways of making the carbene complex. Let us look at another technique now. This is probably a more general technique. We take a carbene precursor which is used in organic chemistry. So, this is a carbene precursor which is used by organic chemists to generate the carbene present in this molecule, and that carbene is in fact this particular moiety that I am going to draw here. So, this is the carbene. This is the carbene that we are talking about, and this can be generated by elimination of a molecule of nitrogen. This molecule of nitrogen can be eliminated, and you can form this carbene. This carbene is in fact stabilized by some resonance with the CO bond, and so it is a stable species that can be generated, and then it can react with this molecule which has got a labile ligand. The labile ligand in this particular instance is tetrahydrofuran. THF is a fairly labile ligand compared to the carbon monoxide, which is also present in the manganese complex. So, if the THF leaves, so if you have minus THF, then minus nitrogen, you eliminate a molecule of nitrogen from here, and if you eliminate a molecule of THF from this manganese complex, you end up with coordination of the 2 remaining species, and you form this nice complex where you have a carbene center coordinated to the manganese. So, this is just an example of how you can use a precursor which a diazo molecule which is a precursor for a carbene to generate it in the coordinations or in the presence of the metal complex, and so the two reactive species react together to form a carbene complex. It is also possible for us to use a different precursor, and that is diazomethane. So, diazomethane can be used as a precursor for CH2, which is also a carbene, which is the simplest carbene that we can think of. So, if you treat this osmium complex with diazomethane, it forms a diazo elimination happens, the two nitrogen atoms leave and a CH2 group is now coordinated to the osmium. So, this molecule also has been made by using a precursor for a carbene carbon, which is familiar to most organic chemists. Now, apart from these reactions, it is also possible to use some techniques which are fairly unconventional. One often thinks that organometallic compounds are not stable in the presence of water, or that they would decompose in the presence of acids. Surprisingly, this is not always the case. Here is a case, here is a system which has got a rhenium ketyl complex. This is a metal complex where you have a rhenium atom coordinated to a CH3CO group, and this CH3CO group now can be protonated with a strong acid, and this trifluoromethane sulfonic acid, triflic acid, can now protonate this oxygen atom. This oxygen atom can be protonated, and that leads to a carbene which is now stabilized by a single heteroatom, which is the OH group, and surprisingly this can be quite stable and can be isolated and characterized. So, this suggests that organometallic compounds are not necessarily unstable in the presence of water. This is particularly true of metal atoms which are either 4D or 5D transition metal series, because they have greater resistivity towards water molecules, and they are more stable towards hydrolysis. And we will discuss this aspect a little later on also. So, we can also have another system where we can deprotonate using a base. In the previous instance, we used an acid to protonate and generate a carbene center. Here, we are going to take an alkyl group which is attached to rhenium, and this alkyl moiety has got a hydrogen atom adjacent to the metal, hydrogen atom on the carbon adjacent to the metal, and these hydrogens are mildly acidic. So, if I use a molecule which can remove a proton, as in this case we have used trityl cation, and trityl cation is an excellent species for removing H minus species. So, here we are removing H minus. H minus is removed from the CH3, and it reacts with PH3C plus in order to generate PH3CH, and you end up with a positively charged rhenium atom which is coordinated to a CH2 group. So, in both instances we have in fact treated either the molecule with a proton and that is what we did here. Here we reacted the molecule with a proton, or we have treated the molecule with a species which will remove a hydride atom H minus to generate a positively charged rhenium complex which is bearing a carbene. Notice that in this particular instance, we do not have a heteroatom to stabilize this carbene carbon. So, this is a system which is called a Schrock carbene. Fischer carbenes are those carbene complexes which have got a heteroatom to stabilize the carbene carbon. The Schrock carbenes are those carbenes which are not stabilized by heteroatoms after the discoverer of this series of compounds, where you have only carbons with non-electronegative substituents on the carbon. So, I now go back to another example of making carbene complexes, and these carbene complexes are now generated by transferring a carbene center from one metal center to another metal center. This can be done if you are moving from a system which has got a 3D metal center and a 4D metal center. Basically, you end up exchanging ligands such that the 4D or the 5D metal center benefits from a stronger metal carbon bond. In this particular instance, we have tungsten hexacarbonyl and the chromium pentacarbonyl with a carbene, which this is a Fischer carbene attached to the chromium, and this Fischer carbene is now transferred to the tungsten. Whether this reaction happens in a bimolecular fashion or whether there is an equilibrium between the carbene and whether there is an equilibrium between this system and the free carbene is not particularly clear, but nevertheless, it is clear that the final product is a tungsten which is coordinated to this carbene, which is also a Fischer carbene. So, this compound is formed by reaction of this chromium carbene complex with the tungsten carbonyl complex, and the tungsten gains this carbene and forms the carbene complex. There is yet another example. In this particular case, because of the presence of light, we are going to generate a coordinatively unsaturated species. FeCO5 is a bright yellow orange colored compound, and if you shine light on FeCO5, it loses a molecule of carbon monoxide and forms a coordinatively unsaturated FeCO4 molecule. This FeCO4 molecule is extremely reactive, and it is able to remove the most weakly held carbene, which is attached to the molybdenum center. So, you have a molecule which has got 4 ligands on the molybdenum, and one of them is weakly held, and so the most weakly held carbene ligand is transferred from the molybdenum center to the coordinatively unsaturated FeCO4, and the FeCO4 molecule now gains a carbene carbon. So, in this instance, you notice that we are moving from a metal atom, which is molybdenum, which is a 4D metal atom, and that 4D metal atom loses the ligand to a 3D metal atom. So, this is apparently contrary to what I told you in the previous example, that the carbene will move from a 3D system to a 4D system, and that is true for thermal reactions. In thermal reactions, this is what you would expect, but because we are having a photochemical reaction, we are generating extremely reactive, coordinatively unsaturated carbon monoxide ligated species, which is FeCO4. This FeCO4 is able to grab the most weakly held carbene, which is coordinated to the molybdenum, and form a nice new complex which has got iron coordinated to the carbene. So, you can transfer the net result that we need to understand is that we can transfer a carbene carbon from one metal center to another metal center. As long as the final result leads to a stable structure, we can always transfer the carbene from one metal center to the other. So, we have been talking about carbene complexes where you have a system with a carbon which has got a pair of electrons, carbon with a pair of electrons, and that carbon donates this pair of electrons to the metal, and the metal has an empty orbital into which it accepts that pair of electrons, and the metal donates a pair of electrons from its filled manifold into an empty p orbital on the carbene. So, this type of give and take between the metal and the carbon is responsible for stabilizing all these carbene complexes. But one has to choose a metal system such that the metal has got some electron density which can be donated into the carbon center. So, in the case of molecules which have for example, a uranium metal center, then it will be very difficult for the uranium, if it is in the +4 oxidation state, for the uranium atom to give electron density to the carbon. That is because it has already exhausted all its valence electrons, and so there would be no electron density on the uranium to form a double bond. So, recently in 2009, a molecule has been synthesized where you have a uranium carbon double bond, and this has been achieved by a particular using a particular trick, and that is as follows. If you have a carbene carbon where there is no possibility for donating electron density from the metal to the carbon center, where there is no possibility because there are no valence electrons on the metal. If there are no valence electrons on the metal and you cannot form a double bond because of this type of a resonance happening, then it is possible that we can get around this problem by making the electron density flow from the carbon to the metal in both sigma and in the pi fashion. So, how can one do that? In fact, before I go further, I should tell you that there are n heterocyclic carbene complexes of lanthanide and uranium, which have been made, but these are systems in which there is a metal carbon single bond. So, there is very little metal carbon double bond character in these complexes. They are best characterized as simple Lewis base adducts of the carbene system with a metal. So, in the systems that we are going to discuss just now, there is in fact a very clear formation of a carbon metal double bond, and that happens because you have generated a carbene or a carbon center which has got electron density both in the sigma and in the pi manifold with a pair of electrons. So, if you have C2 minus, C2 minus, and then both electrons can be donated to the metal in the same direction. Let us take a look at these complexes now. The electron, the bonding picture that we can think of in these cases is the fact that if you have a carbene carbon which has attained an extra pair of electrons, and so that will be a carbene with 2 minus. There is 2 electrons form the 2 extra charges on the carbon. So, you have both a sigma bond, which I have pictured here, that has also got a pair of electrons, and you have a possibility for a p orbital on the carbon, and that has also got a pair of electrons. And the energy level diagram is shown here in the on your left bottom of the screen, and that shows you 4 electrons present on the carbon, and the vacant orbitals on the uranium are pictured here, and they lie at a much higher energy, but both of them are vacant and they can accept electron density. So, these 2 orbitals on the uranium are stabilized by donation from carbon in both a sigma fashion, and that is the sigma fashion here, and also in the pi fashion. So, you have a unique situation where it is no longer a carbene, but it still forms a metal carbon double bond, and this is made possible because of the fact that you have electron donation both in the sigma manifold and in the pi manifold, both occurring from carbon to the metal. So, how can one stabilize the two negative charge, the two extra pairs of electrons on the carbon? If you have a very strong electron withdrawing group on the carbon, then it is possible that the electron withdrawing group can draw away the extra charge that is present on the carbon by pulling electron density towards itself, and this will lead to stabilization of such a dianionic species. So, this dianion is stabilized because you have two ppH2s groups which are present on the carbon. So, let us picture this molecule. This molecule, I can draw this molecule in this fashion. I have P, a pH group, and a double bond S, and I have two of these groups. So, I can draw them like so. And I have 2 minus. This 2 minus charge, this extra electron density, is delocalized on to the phosphorus. So, in other words, you can push these electrons into this phosphorus carbon bond and make a partial double bond, and this can in fact be stabilized by further resonance structures by pushing this double bond and making this an S minus species. So, let us take a look at this molecule. I am going to show you a structure where you have the uranium coordinated to this particular ligand, where you have CR2 2 minus, where the R group is actually a ppH2S. So, here is this molecule. You have a uranium atom, and this uranium atom is present in the place where I am pointing to it with the arrow. So, this is the uranium atom, and it is coordinated to a carbon which is at a distance of 2.326 angstroms. So, you have a carbon which is about 2.326 angstroms from the uranium atom, and you will notice that the carbon is flanked by two phosphorus atoms, and I am pointing to the phosphorus with the cursor, and that is in orange color. So, the orange colored phosphorus atoms on either side of the dark colored carbon is what you are seeing, and the two sulfurs are in yellow. The two sulfur atoms are yellow in color, and I am pointing to them right here, and these two yellow sulfurs are also coordinated to the uranium. So, you have the uranium atom which is flanked by two sulfurs from the ppH2S groups, because you have partial S minus character, which I just explained to you. That S minus character will lead to extra coordination ability for the sulfurs, and so they are pointed towards the uranium, and you have a carbon which is having the 2 minus charge. Now, how do we know that there is a double bond between the uranium and the carbon? The uranium single bond radius is around 1.8 or 1.77 angstroms according to some estimates. And so, if you estimate carbon to have a single bond radius of 0.77 angstroms, you will notice that this distance is 2.326 angstroms. So, it is much less than 2.4 or 2.5 angstroms, which some books estimate. So, because of this shortening of the bond distance between carbon and the uranium, you can say that there is partial double bond character between the uranium and the carbon. It is interesting that in this molecule right here, which I can in fact rotate slightly and show you, this is a beautiful molecule where the uranium atom is in fact surrounded by 2 BH4 units, BH4 minus ion units, and the hydrogens are in fact pointed towards the uranium. So, you can see the 3 hydrogens that are on the BH4 units, they are pointed towards the uranium. They are also coordinating to the uranium, and you have these 2 sulfurs coordinating. In addition, you have the carbon, which we are interested in this lecture, that is coordinated to the uranium as well. So, here is a case where you have a very strong indication of the formation of a double bond between the uranium and carbon. Getting back to this particular structure, I would like to show you another molecule where also you have evidence for some carbon uranium double bond character, and that comes from a different structure which was characterized fairly long ago. But this is not a system which has got 2 negatively charged 2 electrons on the carbon. This is in fact a system where you have a CH2 minus, and you expect a distance of 2.6 angstroms, and the uranium carbon distance. This is the carbon distance. This is the carbon that we are talking about, and this is the uranium atom that is present in the structure, and this distance is around 2.29 angstroms. So, there are instances where you can form short uranium carbon contacts, and these are indicative of the fact that even in the case of uranium, you can have stabilization of the MC double bond, and these are relatively rare, but nevertheless it is possible to have this double bond character between the actinide or lanthanide element and the carbon center. So, let me now move on to another system briefly, and that is a carbene system. This was accidentally discovered, and the reaction of the Fischer carbene with BX3 or a trihalo boron molecule BX3, BCl3 or BBr3 led, instead of a substitution of this OCH3 by the X group, instead of converting the OCH3 to an X group, one ended up with elimination of the OCH3, leading to the formation of a carbene complex. So, carbenes are relatively tricky to understand because of the fact that you have now a molecule which is apparently a neutral donor, and you have the possibility for forming 3 bonds between the tungsten and the carbon. So, let us take a look at some of these molecules, how they are made, and this would have a net positive charge and BX3 OCH3 and a negative charge to compensate for the extra halogen atom on the boron. So, you could also do the abstraction of a proton or a hydride. In this particular instance, this molecule is polarized in this fashion. You have CH2 minus and a PPH3 plus. You can write it in this fashion, and this can abstract this hydrogen which is on the vinylic position, leading to a tantalum carbon triple bond. Now, let us take a look at these molecules, and once again let me show you this molecule which is pictured here. This is a tantalum carbene complex, in which you have the carbon at a very short distance of 1.849 angstroms, and so this is a distance which is assumed to be a triple bond. It is much shorter than a metal carbon double bond, and it is much shorter than a metal carbon single bond. And so, the best formulation of this molecule is to assume that you have a triple bond between the metal and the carbon atom. So, let me now proceed further. Here you have the picture of this molecule, where you have the benzene ring attached to the carbon, which is attached to the tantalum, and you can see that the distances are very short. So, you have metal carbine complexes, just like you have metal carbene complexes, and they can be made in a variety of ways. I will show you quickly two different ways. One is to use a ylide to abstract the proton. Another is to use sodium amalgam again to reduce the tantalum oxidation state of the tantalum from what it was earlier, by eliminating this bromine as sodium bromide, and this sodium bromide is eliminated, and you form a tantalum carbine complex. Here is one more instance where you can have a CCl2 group attached to the osmium, and we have done a substitution reaction with aryl lithium. It can be any aryl group, but phenyl lithium would do, and you can end up with a carbine complex that is pictured here. We have looked at several compounds where the metal is bonded to the carbon. The bond order has changed from 1 to 2 to 3. Now, is it possible to have just carbon as a ligand? We will see this in a future lecture. We have looked at the possibility of a carbon metal bond order of 3. Can we have a quadruple bond between the metal and the carbon? This is again something that we need to explore later as well. So, to summarize, let me say that we looked at heteroatom stabilized carbene complexes. We looked at n-heterocyclic carbenes, and the key points that we have learnt is the following. Carbon can have multiple bonds between the carbon and the metal, and we can have synergistic interaction between the metal, so that you can have a give and take which stabilizes the metal carbene complex. And if the ligand can be stable, made in a stable form, then it is easier to make these molecules and study them in the coordination sphere of the metal. So, metal carbene complexes and metal carbene complexes have been extensively studied and are very useful species in organometallic chemistry.